In chemistry, we explore three states of matter: solids, liquids, and gases. Here I am using the PhET simulation from the University of Colorado to model the solid state of oxygen. The way that we know it's a solid is that it has defined shape, defined volume, and these particles are not moving around a whole lot. The only particle movement we have is vibration. So they're all vibrating in place, but they're not really sliding past each other. They're not moving around very rapidly. Right now, I'm going to heat that solid, and as it absorbs that heat, notice that the kinetic energy of the particles increases. So they are moving faster and faster. And now that solid is turning into a liquid. The way that we know that it's a liquid is that the particles are still fairly close to each other, but we have a lot more molecular motion. So we have defined volume, but undefined shape. Notice that the shape keeps changing as the particles move around, but they still have pretty close contact to each other. Now, if I keep heating this sample and I keep increasing the kinetic energy of the particles, eventually that liquid will turn into a gas. And that process where the particles absorb energy and they absorb heat and they turn into a gas, we call that the heat of vaporization. The process where they go from a solid to a liquid, we call that the heat of fusion. And we're going to explore these terms a bit more rigorously so that we can do some calculations. We're also going to plot these processes on a graph that we call the heating curve. So we'll take a look at all of that. We'll take a look at the equations, but I think it's a good idea to have a visual understanding of what is actually going on in the particles before we get into all of that. In our phase change model, the first thing we saw is that the oxygen melted from a solid into a liquid. That's what we call the melting point. So the temperature at which a solid melts is the melting point. And more rigorously defined, the melting point is the region where particles gain sufficient energy to overcome the attractive forces that hold them together. So as the particles lose those attractive forces or break apart those attractive forces, they start to move faster and faster. And that process is what we call the heat of fusion. So heat of fusion is the energy that must be added to convert exactly 1 gram of a solid to a liquid at its melting point. So there is an equation for heat of fusion, and the exact number is going to vary depending on the substance that we are concerned about. So most typically we deal with the heat of fusion of water. So the heat of fusion of water is 334 joules per gram or 80 calories per gram. So heat can be expressed in either joules or calories, and these are the two different values for water. So this delta H fuse that I'm writing here, that is representing the heat of fusion. So if we are calculating, for example, let's say that we are trying to melt 50 grams of ice, and we want to know, well, how much heat do we actually need to apply in order for all of that ice to melt? The equation that we would use is Q is equal to M times the heat of fusion. So Q here represents heat, and heat can be expressed in joules or calories, and of course, kilojoules or kilocalories. M is representing mass, which is typically expressed in grams, and delta H fuse is representing the heat of fusion. And heat of fusion is just a value that you would look up in a table or in your textbook for each particular substance. Similarly to melting and freezing, we can also vaporize or condense substances. And the reason I'm lumping all of these processes together is because they really occur at the same temperature. They are just going in opposite directions. So for example, when we're looking at melting and freezing, both the melting and the freezing point of water is 0 degrees Celsius. Now, whether you call it melting or whether you call it freezing depends on which direction you are going in on the graph. Same sort of thing with vaporizing and condensing. So the boiling point of water will be the same as the condensation point. The only difference is which direction we are going in. So the heat of vaporization is defined as the energy needed to convert 1 gram of a liquid to a gas at its boiling point. So here we are vaporizing the liquid water. And the heat of vaporization is 2260 joules per gram or 540 calories per gram. So which value you use depends on which unit you are interested in when you're doing your calculations. Now, the heat of vaporization can also be used when you're doing condensations because it's the same temperature. It's only a difference in direction. The equation for the heat of vaporization is Q is equal to M times the heat of vaporization. So that is the equation that you would use when you are trying to figure out how much energy you need to apply in order to vaporize a substance. So Q here represents heat, and those units will be in either joules or calories. M represents mass, and that delta H vap represents the heat of vaporization. So the values that we listed above. It looks very, very similar to the heat of fusion, and you would use it in a very similar way. The only difference is that the heat of vaporization is a larger number. Now that we have defined all the terms and we saw visually in the simulation what these particles actually look like as they absorb heat, now we can put all of that together and explore the heating curve of water. So this is a graph that's going to track the phase changes as water absorbs heat. Now, there are a couple of temperatures I want to highlight here, and that is 0 and 100 degrees Celsius. The reason those are important is that 0 degrees Celsius is the freezing and melting point of water. 100 degrees Celsius is the vaporization and the condensation, or the boiling point of water. So that's where vaporization and condensation will occur. So those are two important temperatures. If we go below 0, we are, of course, cooling our water. If we go above 100, we are heating it up even further. So if we are below 0 degrees Celsius in this region, well, water is going to be a solid, right? If we are below 0, it will definitely be ice, which is solid water. Now, if we are starting at less than -20 and we add heat into the system, water, or that solid ice, is going to absorb heat, and it's going to get warmer and warmer and warmer. And notice that that temperature is increasing. So as I am adding heat, on the x-axis, the heat is being added, and as we go left to right, the heat is higher and higher, which can be expressed in joules or calories. And on the y-axis, I'm tracking temperature in degrees Celsius. So as I'm adding heat to the right, notice that the temperature is increasing. So we're going from below -20 all the way to 0. So in that region, as heat is being added, the temperature of the sample increases. Now, once we hit 0, we are hitting the melting point of water. So before that, as the ice is in its solid form, there is no phase change yet. We're going from a very, very cold chunk of ice at about -20 to a chunk of ice that is about to hit 0. So here there's no phase change, it's still solid. All it's doing is warming up. And because there is no phase change, all we're really doing here is changing the temperature of the sample. And the equation we would use to calculate the heat for that process would be Q is equal to mass times specific heat times the change in temperature. And this is probably the trickiest part of dealing with heating curves and cooling curves, is trying to figure out which equation to use for which process. So if there's no phase change, use the standard heat equation that has the mass, the specific heat, and the change in temperature. Once we hit 0, as we add heat, there's no temperature change because at 0, we are melting that ice. So notice that here I have a flat line on the y-axis, and that's because the temperature is not changing. It's going to stay at 0 until that ice completely melts. And that process is what we call the heat of fusion. So here we have a mixture of ice and water. And the temperature is not changing. It's going to stay at 0 degrees Celsius until that ice is completely melted. And because that's happening, you can't use an equation that has delta T in it because there will be no change in temperature. So that equation wouldn't really make sense here. The equation we're going to use is the one that uses the heat of fusion. So to calculate heat here, we're going to use the mass of the ice, or the whole sample, times the heat of fusion. And that is because here we do have a phase change. We are going from a solid to a liquid. Now, once that ice has completely finished melting, so we are now looking at this point right here, it is now liquid water. And if we keep adding heat to that liquid water, well, the temperature is going to increase. It's going to absorb more and more heat, and it's going to warm up. So here again, we're looking at a liquid, and we don't have a phase change. So as we're adding heat, we're going from cold water to very hot water, but it's still water. It has not changed phase yet. And because there is no phase change, we're going to use the equation Q equals mc delta T. Now, once we hit the end of that process, so once we reach 100 degrees Celsius, which is the boiling point of water, that liquid is going to start changing into gas. And this is what we call the heat of vaporization. So here we have a mixture of water and steam, which is both liquid and a gas. We have a mixture. And here we do have a phase change. We're going from a liquid to a gas. And anytime you have a phase change, the temperature is not changing. It's going to be at 100 degrees Celsius throughout that whole process, which means we're not going to use the equation that has the change in temperature. We're going to use Q is equal to M times the heat of vaporization. Once that process is finished, so when we have completely vaporized the sample and everything is gas, then we're going to be in the gas phase. And if you keep adding heat, you're going to keep increasing the temperature of that gas. So here again, we don't have a phase change. Everything is in the gaseous state. And since there's no phase change, we're going to use that same equation, Q is equal to mc delta T. So this is the process for figuring out where you are in the problem. And whenever you're doing these type of phase change calculations, I recommend sketching out a heating curve of water and trying to track where are we in the process, because that will help you dissect which equations you need